Okay, so let's pick it up from where we have stopped. I left a question for those who are joining us now. Jaden and there's somebody else. I'm not sure what the name is. Some of those names are written using very funny characters. We left a question here on radioactive decay series, and I said that a radioactive decay series happens when one nuclide disintegrates or decays, forming a new nuclide, and the new nuclide formed also happens to be unstable, so that then it disintegrates, forming another one, so that the other one also, if it's unstable, continues disintegrating, and we have a series of such steps. That is what we call a radioactive decay series. And we said that in case of such a series, these unknowns can be found simply by calculation, just like we did when we were talking about one equation like this one. So let's go through the solution. Those of you who have tried that in your books, check and confirm whether what you have done is the correct thing by comparing whatever you've done with whatever I'm doing here. So this is the first nuclide decaying to form a new nuclide. The number up here is 232. The number up here is 228. They need to balance for both sides. This reagents or reactant side and the product side. So for this equation to be balanced, I'm going to pick just this part. I'm going to pick that part. So there is TH disintegrating or decaying to form Ra plus X. Plus X, just a minute. Plus X. So this X has a number A here and it has a number B here. This number A here is the number that will add to 228 to give us 232. This is going to be 4 because 4 plus 228 should give you 232, and the number down here obviously will be 2, so that 2 plus 88 gives you 90. So the kind of radioactive decay happening in the first step is alpha decay, and the particle here is that one. So this is alpha. This is alpha decay. In the second step, we have Ra decaying to give us AC, and the kind of radiation taking place here, or rather the radioactivity taking place here is releasing a particle A that we are not sure what that one is. So this is 228, and on the other side we have 228 as well. So this is AC plus A. A has a number up here, which you add to 228 to give you 228. So this is obviously going to be 0. And the number down here is 89, and you're going to add it to another number X here to give you 88. So this is going to be -1. So this obviously is an electron, because we said an electron will be indicated this way. Remember our previous lesson. So this is beta decay. And then finally we have AC decaying to give us B and releasing beta particles. So what is B? What is the identity of B? B has a number here M and a number here N. So the mass number is going to be M plus, because this is a beta decay, this is going to be an electron, 0 and -1. So M here plus 0 should give you 228, and therefore M becomes 228 as well. N plus -1 should give you 89, and therefore N becomes 90, like that. So that is the kind of thing that we're going to see. And our series could continue. This could continue so that we have gamma radiation being released there, forming C, and somebody wants you to tell us what the mass numbers and atomic numbers are in this case, and you tell that person that C has the same numbers as B, 228 and 90, because alpha decay or alpha radiation isn't composed of particles. It is just energy without particles, and therefore we do not have mass numbers, we do not have atomic numbers like in the case of alpha and in the case of beta. Instead, it is just radiation without any particles. And this series could continue on and on and on until we get a more stable isotope. Alright, so unless there's a question, I will not continue with radioactive decay series anymore. But if you have questions, comment them there. Comment them there so that we can help you. Those who are on Zoom, yeah, you're not on mute, so if you have a question, you can ask. Alright, so the next thing that we talk about is something that we call comparison between the reactions that take place under this category of changes as compared to chemical reactions. What are the differences between nuclear reactions and chemical reactions? And as I said, chemical reactions involve loss and gain of electrons, while nuclear reactions involve changes even within the nucleus. That means that in the case of chemical reactions, you're never going to form a different atom or a different particle. What I'm saying is, if you have a compound X, Y, Z reacting with another compound Q, W, P, you cannot introduce another atom J here. You are going to just be interchanging these things so that you will form a new compound XW plus a new compound YP plus whatever else, but you will never form a different thing. If this is carbon 4 oxide reacting with something like maybe zinc, there will just be a redox reaction. The zinc could take the oxygen from this carbon 4 oxide so that you form carbon, but you will not form PB here. In this case of nuclear reactions, you can, and we have said, or we have seen, that this compound is forming another compound, etc, etc. That is the first difference. Is that a question, Jaden? Are you okay, Sandra? All right. So in the case of chemical reactions, the changes take place within energy levels, changes in energy levels, and involve changes take place within energy levels and involve only electrons. In this case, changes take place within the nucleus of that atom, and they involve, so in. So the changes involved in nuclear reactions take place within the nucleus, and they could involve neutrons as well as protons. Another difference is that in the case of chemical equations, the changes in energy are very small, so that you can measure the changes are in temperature, for example, using a thermometer. So they are very small changes in energy. But in the case of nuclear reactions, the changes in energy are so huge that at in some cases they are destructive. And I remember last time I gave an example of an application of nuclear reactions in making bombs. The amount of energy released is so much, it is enough to bring down a whole building or even to flatten a town. In the case of chemical reactions, the energy released is very small. So small changes in energy. Great. Changes in energy. The changes in energy are very small in the case of chemical reactions. The changes in energy are very huge, or yeah, they are large in the case of nuclear reactions. We have also said another difference is that no new elements are formed in the case of chemical reactions, but in the case of nuclear reactions, new elements are also formed, and you can see I've explained that in terms of neutrons, protons, and electrons. Why new elements would be formed here, why new nuclides would be formed here, and why new nuclides or new elements would not be formed here. Another difference is that chemical reactions are affected by environmental factors such as temperature, such as pressure. There's a topic in Form 4 called rates of reactions, and in that topic you learn that the rate of a reaction can be changed if you increase, for example, the temperature, if you increase the pressure, or lower them depending on the kind of reaction that you're talking about. So in a chemical reaction, the reaction could take place faster or at a lower rate depending on what you change, the pressure, the temperature, or any other environmental factor, the concentration, etc. In the case of nuclear reactions, those changes do not affect the reaction, so not affected. So chemical reactions are affected by pressure, temperature, etc. Depending on, are you involving, do you have a reaction involving gases? Are they solutions? Are they solids? There are all those things that are taught in that topic. That is. Yes, there's a question. Sorry. Speak up. Oh, you're not able to see the board. The board. All right. Let me see what I can do for you. Let me see what I can do for you. All right. Give me a minute, Jaden, so that I get assistance, and the board will be zoomed for you. Just a minute. All right. So in the meantime, when I'm not able to, as we wait for the person operating the camera to zoom, I will try to write larger letters and numbers here so that it becomes more clear. All right. The next thing that we learn today is going to be radioactive decay. Is that better? So the next thing that we're going to learn is about radioactive decay and half-life. And we have said all along that when a radioisotope undergoes radioactive decay, it forms a new substance. That means that the substance that we had initially is going to be or rather the mass of the first substance, the amount of the first substance will start to decrease. An example is, let me just pick an example, the ones that we used last time. Consider this. That is uranium-235. Undergoing some so that it forms a whole different thing. So plus X, plus Y, etc. Consider that. Plus, of course, so many other things. At the beginning, we could have 40 grams. 40 grams. We could have 40 grams of the first substance here. But as the decay continues, we're going to have less of this one and more of this. The unstable nuclide, or the atoms or nuclides of the unstable element here, or isotope, will disintegrate, forming a more stable one until we have no more of uranium, of U-235 here. So, radioactive decay, therefore, destroys one substance that is unstable and forms a whole new lot of substances that are more stable. Now, in radioactive decay, half-life refers to the time taken for this mass, the mass of uranium or whatever other substance you're talking about, to decrease from 40 to 20, from 100 to 50, from 10 to 5, from 2 to 1. So when the mass, or the initial mass has reduced to half of whatever it was initially, we say that, or rather we call that time the half-life. And the half-life of different substances could range from years, or actually millions of years, to a second. We have those substances that decay very fast, and we have those ones that take so much time, so that it will take a lot of time for them to decrease by half. Mr. Mushera, kindly zoom for me. The people on Zoom are telling me that they are not able to see the board clearly. So you can get Madam Theory to film the other one for us while you try to make Zoom better for the other students. All right. So I was saying, yeah. Our students on Zoom, are you able to see us now? Is the board better? Is it better now?
Much better.
All right, good.
Much better. Correct English.
All right. So I was saying that half-life is the time taken for the initial mass to reduce to half of whatever it was. I was saying that some substances have a very long half-life, while others have a very short half-life. I could give examples here. There's a substance, a radioisotope, known as palladium, and because we said that some of these substances are not among the first 20 that you learn in the periodic table, I will not bother you with the properties and characteristics of those substances. I'll just give you the symbols. So I could give examples. For example, this one called PO212. It has a half-life of these many seconds. So that if you had 10 grams of palladium, after after this time, we're going to have half that mass. So that is a very short half-life. On the other hand, we have this element. This is an isotope. So this is an isotope of carbon, and we are familiar with carbon. If I was to give you 10 grams of carbon, for that 10 grams of carbon to reduce and to become half, it would take these many years. So it would take 5,570 years. So the half-life of carbon is very long. The half-life of palladium is very short. So the half-life could range from very few seconds, actually microseconds, to very many years. and depending on how short or how long the half-life is, the radioisotope is used for different uses, because of course sometimes we want a radioactive isotope that decays very fast for a given application, and we want another one that doesn't decay very fast for another different application, and etc and etc. So I hope that is understood. Now, questions around half-life could appear in different formats. Let me just give you a number of ways in which an examiner could give you a question on half-life. Consider a radioisotope whose half-life is what? Let's say I'm trying to create just a radioisotope whose half-life is 8 seconds, and you have 10 grams of that radioisotope, 10 grams of radioisotope X, and the half-life, we call it T half, is 8 seconds, like that. So how long would it take for these 10 grams to decay so that we only have 2.5, for example, 2.5 grams? There are two ways of answering that question. You can use a formula, or you can just break it down in terms of half-lives. And I'm going to use the method where we break it down into steps, half-lives, so that eventually we have 2 grams. Now you have 10 grams of X. After one half-life, we are going to have only half of this, and that is 5 grams. This is after 8 seconds. That is one half-life. After another half-life, these 5 grams will decay so that we only have 2.5 grams, and this is another 8 seconds. So the question would be how much time is required for these 10 grams to decay so that we only have 2.5 grams left, and that is of course 8 seconds plus another 8 seconds, and the answer to that question therefore is 16 seconds. The question could also be in the different, or in the reverse, so that you're told that, for example, you have let me use something like carbon. Let me pick something different. Let me use an element Q. An element Q has half-life X that we don't know, so we are required to find X. Now we had 100 grams of Q, and then after 100 days, these 100 grams, they had reduced to 12.5. Yeah, 12.5. So what is the half-life of Q? After one half-life, this mass becomes 50, because after one half-life, whatever you had initially will go to half. So many atoms, so many nuclides of Q have decayed so that we only have 50, forming new substances. So this is one half-life, and the half-life is X. After another X years, then we have 25 grams. After another X years, or days or months, we have 12.5 grams. Now the question is, if it took 100 years for 100 grams of X to become 12 grams of X, so that all the other atoms had decayed to form other things, what is the half-life? So 3 half-lives are equivalent to 100 days. So what is one half-life then? That becomes 33.3 days. So the half-life of Q is 33.3 days, because this is 3x, which is equivalent to 100 days. So what is there for X? And from your basic mathematics, you can see that X is going to be 33.333 days. It's a recurring number. So the half-life of X is that figure. So an examiner could twist the question in those different ways. You could even be taught to calculate the percentage of Q remaining after maybe 4 half-lives, or the percentage of this was X remaining after, for example, maybe 24 seconds, and the approach would be the same. That you would ask yourself, after 8 seconds we have 5, after 8 seconds we have 2.5, after another 8 seconds we have 1.25 grams. So somebody could tell you to tell them or to calculate the percentage of X remaining after 24 seconds, and that is what you have here. So your answer would be 1.25 over what you had initially, which was 10, of course, times 100, and that becomes your answer. That is the percentage. So there are so many questions that could be set around this work, but all of them require the same approach. Now, finally, I'm looking for my dust. Finally, half-life could also be calculated in a different way, and the different way is in terms of measurement of how many disintegrations are happening per unit time. We learned with a different teacher yesterday, those who joined us in physics, that radioactivity, I think it was they were learning about gamma rays and stuff like that, and the content taught there was that radioactivity is measured using an instrument that is known as a GM counter. A GM counter, that is a gigamolar counter, and it is an instrument that is used to tell you how many disintegrations are happening per second. And of course, the number of disintegrations or rather decays happening per second will depend on how many particles we have. Take for example the radioisotope I had here, that is TH, and we have for example 20 kilograms of TH. We have millions and millions of nuclides of TH, and all of them are decaying or disintegrating. And therefore, if you were to bring TH, or rather 20 grams of TH, and place it in front of a GM counter, the GM counter would record a very high degree of activity. It would tell you that so many disintegrations are happening. If you took the same TH, but now you're dealing with maybe only 0.05 grams